In the first 3 months of 2026, a barrage of automated traffic slammed into central server nodes across the internet. The target was the world's largest code repository. GitHub suffered at least 8 major system outages, failing to maintain its standard 99.9% uptime metric. If you looked at the server logs, this had the signatures of a massive DDoS attack. However, there were no bad actors or botnets involved. The traffic was generated by legitimate, autonomous AI coding agents. They were executing their tasks exactly as designed, but at a volume human infrastructure was never built to anticipate. This chart shows the scale of the anomaly. Weekly commit volume spiked to 275 million, approximately 4.5. The February 9th incident illustrates the specific technical friction. GitHub's DevOps team executed a routine optimization, reducing the user settings cache refresh window from 12 hours down to 2. That minor configuration tweak triggered a cache rewrite storm. The authentication database was overwhelmed by rapid-fire requests, bringing the entire platform to a halt. This diagram shows the root cause. On the left, the traditional human workflow, a slow path to a single pull request. On the right, the agentic harness. The AI generates code and iterates hundreds of times per minute. Every micro-adjustment hits the server as a literal commit, causing it to overflow. Faced with this load, GitHub's initial plan to scale capacity by a factor of 10 was insufficient to keep the service online. Engineers eventually implemented aggressive backpressure, traffic degradation protocols, and strict fault isolation to keep individual rogue agents from causing cascading network failures. As machine-driven writes begin to dwarf human commits, these repositories are increasingly functioning as high-frequency scratch pads for automated reasoning. The technical failures of the infrastructure led to a mandatory change in the platform's economic structure on June 1st. Legacy per-seat subscription models became unsustainable once individual agents began submitting thousands of commits per day. GitHub moved away from fixed seat costs towards AI credits, anchored to the tokens consumed. By doing this, GitHub is reclassifying software development as an automated pipeline, where the primary cost driver is compute volume. As machines generate and test the bulk of the code, human developers are increasingly pushed to the edges of the network, acting strictly as reviewers. Controlling the velocity and quality of autonomous machine output has become the primary engineering challenge. If these agents operate at this massive velocity, the critical risk is they optimize themselves into catastrophic logic errors. Early systems were susceptible to magic mutation. If an AI discovered a novel fix, it often had permission to directly rewrite its global instruction files. While this is adaptive learning, a single hallucination in the instructions is immediately solidified into the system's long-term logic, affecting all future tasks. To manage this, OpenClaw version 6.1 provides a rigid protocol-level constraint against these unvetted updates. In the new architecture, when an AI agent attempts to write directly to the global execution logic, it is blocked. Instead, the agent routes new knowledge through a skill workshop tool, formatting the data into a structured skill proposal. This proposal is bound by immutable versioning, hash checksums, and a specific command set. Finally, it enters a quarantine queue. The new skill cannot be activated until a human operator authorizes the merge. Autonomous self-optimization in production carries too much risk. Maintaining stability requires forcing AI updates through human-gated, deterministic pipelines. These protocol-level constraints are even more vital in the realm of enterprise business data and financial querying. Unlike software code, a query about quarterly revenue has a singular, objective, and absolute mathematical truth. The tolerance for error is 0. When large language models fail in this environment, it is usually due to specific engineering failures rather than weak reasoning. In this failed SQL query, the model failed to map the human phrase customer churn to the obfuscated column name in the database. These semantic mapping failures, along with stale data states and vector retrieval errors, drive the majority of hallucinations. Engineers at Anthropic found that prompt engineering and large context windows cannot resolve these fundamental routing and state errors. Interfacing unstructured models with structured corporate data requires a dedicated translation layer. Anthropic's solution involves a multi-tiered semantic layer stack rather than reliance on complex prompts. The architecture starts with a data warehouse base, capped by 4 distinct, rigidly defined trust tiers for data sources. The skill modules sit on the next layer. These consist of pre-written, human-verified code templates, such as specific SQL chains and valuation formulas, that execute deterministically. These modules function as a translation layer, mapping AI semantic flexibility onto the database's rigid schema. The performance metrics show why this layer is necessary. Without these skills, the smartest raw language model achieves only a baseline accuracy rate on complex corporate queries. When the model is constrained by these skill modules via the Model Context Protocol, accuracy reaches a consistent peak. Maintaining these skills is a primary engineering task. It requires automated testing and regression checks for every database change, preventing data drift. Operating safely in the agentic era requires treating LLMs as volatile compute engines. Ensuring accuracy means integrating them into deterministic infrastructure, where every machine-generated output is constrained by engineered logic.